So here we have our first homework session. I have 6 exercises for you that cover the topics of the logic and the proofs videos. In exercise 1, you are to work with truth tables, and I've given you some logical formulas here, and you have to complete the truth tables for them and see if you observe something interesting there. Number 2 introduces another logical operation, the so-called exclusive OR, which is denoted by this symbol, and the truth table is given as stated here. So the logical operations we got to know in the video are not the only ones that exist, there are more. And your task here is to express these XOR operations using one or more of our logical operators from the video. The third exercise is an exercise in negating quantified propositions. So here I wrote out a proposition which has a universal quantifier and an existence quantifier in it. First, you are supposed to write this as a logical formula, then negate it, and finally decide whether the original proposition or its negation is true. In exercise 4, you should prove that n squared plus 3n plus 2 is an even number for all natural numbers n. You could try doing this by induction or just doing it directly. Exercise 5 is similar to what we did in the videos. In part A, given some natural number n, we are supposed to prove that 3 divides its square, n square, if and only if 3 divides n. You might remember that we had something similar with odd and even numbers, so that was 2 divides n square if and only if 2 divides n, and here we have the same with 3. And we could use this in part B of exercise 5, where we're supposed to show that the square root of 3 is not a rational number. Recall that in the videos we showed that the square root of 2 is not a rational number, and we can very similarly proceed here to show that the square root of 3 is not a rational number. Finally, in exercise number 6, you should practice proofs by induction. So in the first part A, there's a sequence an which is defined recursively, so I give the initial term of this sequence, a1 equal to 5, and then I say an is defined depending on an minus 1 and on a1, where a1 is just constant though. So in order to get the nth term of my sequence, I first need to have the n minus first term. And what we should prove is that we have a closed form formula for this recursively defined sequence, and it is this one, an equal to 5 over 7 times a to the power of n minus 1. And of course you should use induction for that. And in part B, it's a bit similar to the Gauss summation formula. It's a bit more complicated. Here we sum over the squares of the numbers from 1 to n, and we are expected to prove by induction that the sum of the squares from 1 to n is the same as n times n plus 1 times 2n plus 1 divided by 6.